So, alright, so this is some mathematical work that I did with Edward Kerr, who is at Baron-Champaign, and Mark Wilkinson in Oxford. And basically this is motivated by some fascinating, I think, physics questions, and we have only some very crude and rather naive mathematical understanding and answers. Hopefully this is the beginning of an equally fascinating mathematical journey, but this is really the very crude beginning now. And in some sense, I understand very little about the physics, and mathematics that we have don't really match the physics that is supposed to be there. So, you know, I figured that since I have a lot of questions, the best way to ask, you know, a lot of experts is to gather them in a room and say that I'm going to give a talk. So don't be too disappointed. There will be plenty of questions for sure, which I think they're very interesting. So one of the motivations for what I'm going to talk about is related again to defects and what's the relation between small and large scales. So you have these obvious features in nematics, these defects, but you know they are on very small scales, and you have trouble understanding what they are at their core and their essence, because if you get too close, then you know all the experimental techniques break down. And then the question would be that is there some kind of large-scale manifestation, something that you can measure out of these defects without having to get too close to the core. And you know, if you think in terms of the mathematical description, like what we had yesterday, these director descriptions, you realize that if you work with something like directors in the plane, the presence of defects will create frustrations. Namely, you try to put together these anisotropic objects, so they will create larger scale disturbances which can be measured energetically. They have an energetical signature. Otherwise said, there is a lower bound on the energy expressed in terms of the degree in 2D. If you relax things a bit and you go in 3D, things are not so good. This energetical signature is gone, and you know, you can play the devil's advocate and say, okay, if I'm going to relax things even further, namely working with Q-tensor, will there be an energetical signature, a large-scale signature of these defects? And you know, I come back to this thing that I tortured you yesterday with the low dimensionality curves. Maybe these defects have an energetical signature, a large-scale signature, only if you work with low-dimensional objects, but not if you work with high-dimensional objects. So is there like a way of asking the nature, you know, what it really wants to do? Namely, is there a relation, a real relation between defects and large-scale structures? Yeah. So let me show you the most interesting part in this talk, which is a movie. Okay. You see, it's done nearby. So it's about isotropic to nematic phase transition. There will be two movies. The second one is actually more relevant, perhaps, to what I'm going to argue about. So, you know, overall, there are large-scale structures formed when you go from isotropic to nematic. This is at a coarser scale than the next one, which is actually more interesting. So you observe these nematic islands that form into the black isotropic environment.
So is this a simulation, or is this a real?
It's a real thing. It's a real thing. Yeah. Real. You can find it on their webpage. Oh, pretty huge. Pretty huge. Okay, so this is the real thing, yeah. That's what actually happens. And now the trouble comes when you try to mimic it with mathematics. Oh, come on. Okay, so the claim is that this sudden quench, so you drop suddenly the temperature in an overall isotropic material, and then it turns into nematic, and this appearance of nematic happens through the creation of these islands that, as you saw in the second movie, increase in size. And the claim is that if you wait long enough, you see a scaling phenomenon. The pattern of domains at a later time looks like the one at earlier times, just you change the scale, right? And this happens only in a statistical manner. Okay, that's the important thing here. So you need to look at things on average in some sense, and that's what I found as a claim in this paper of Bray that I've been looking at since like 2007. There it had like, at that time it had like 1,000 citations. Now it has like 1,600. So by the popularity metric, this should be a very good paper. Somehow I don't really understand much out of it, but let me tell you that there are various very interesting claims there. So I don't know, how much people agree on this in the physical community, but I'd be interested in knowing what the opinions are. So what I'll do is to go through some of those claims and tell you why I think they are interesting and presumably tractable, hopefully mathematical questions, and what we can actually do so far. So there is this quantity called the correlation function, which is something like this here. So you look at basically the relation between what happens at x plus r and what happens at x, yeah, and you average over the x's, yeah. That's what these angles stand for. And you also average over the initial condition. So, you know, if you have some anomalous initial data that causes you trouble, then that kind of average will, will destroy that anomalous initial data. And of course, you also rescale things. So this corresponds to r is equal to 0. Yeah, the quantity that you have on top. But now it's r is equal to 0. So this gives you a quantity that measures overall correlations at distance r. Yeah, quantity that evolves in time. So time dependent, and it's a very crude measure of what happens. How much difference is between two different points if you average, over all possible pairs of different points distance r, and over all possible initial data. Okay, there is also the Fourier transform of this sk of t, and that hypothesis of having statistical self-similarity is translated into the fact that the correlation function should assume a scaling form, something like this. Yeah. So this L of t is supposed to be the length of, the average diameter of a nematic island at time t. Okay. And of course, if you just formally say that you have equality and you take Fourier transform, this is what becomes in the Fourier land, that hypothesis. And now, can you actually see this out of the equations? There are some interesting statements. First, Bray talks about the ON model, which he defines as a model described by vector field with n components, and then associated to it there's an energy function that is invariant under global rotations of phi, and then you can consider a gradient flow for that. And there is this so-called Porot's law, which tells you how the Fourier transform behaves, right? And this is for large enough frequencies, right? So on small scales. And in here, D is the dimension of the space in which you work, and N is the N from ON. Now, this is a more complicated object than your correlation function that we had before. I mean, it's just the Fourier transform, but you know, you don't look at. I mean, in principle, if you know the correlation function, you know the Fourier transform, right? And the other way around. But here you look. Sorry. Yeah.
What kind of a law is Poirot's law?
This is the claim that this happens.
It's a claim, so it's a hypothesis. From
Yes.
the law.
Yes.
Okay.
Yeah. So yeah, you have this presumed behavior, and also there should be something more here. Namely, you should not look at all very long, very high frequency, but you should stop at some point, because if you work with analytic functions, then you have terribly fast decay. You don't have these fat tails. So you should take care when interpreting this presumptive law, and that's why this is a much more complicated object than the correlation function before. And also,
excuse me.
yeah.
You showed us a similar one previous slide.
Yeah. Yeah.
Could you go on? So different possible the lowest one.
In principle, formally, if I have this, I put equality, and I take Fourier transform, I would get something like this, where G is the Fourier transform of that.
I think the point is that L to the D is just a trivial volume factor for the Fourier transform. I don't think it has any physical.
Yeah, no, that's
okay.
true. That's
This
true.
next one. And
This is
question.
the physical.
Usually
part.
in
Yeah.
physics, some anomalous dimension appears. Anomalous, but it means not integer.
Not what?
Not integer. Not the integer. Power of the.
Yeah, no, they get logarithmic corrections or weird things here.
Okay.
No problem.
We'll later.
Yeah.
See. Okay.
No, the physicists need to get them, but it's a bit harder to find it. The simulations, okay? Just to see how you could get, on a mathematical level, this kind of behavior, it has to do with having high enough gradients, right? The fact that you have high gradients but still analytic behavior means that eventually the end of the tail will decay fast, but there is part of the tail that behaves like this. Okay, so that is quite mysterious, because there are these high gradients which are supposed to be associated with topological defects, right? Assuming that topological defects have this energetical signature, and these somehow small-scale defects should have a large-scale signature captured in this thing here. That's somehow the claim that you'd find hard to believe, and I did at least. But this is a quantitative way of saying that defects, have a large-scale effect. Yeah, and of course this is all hypothesis, but there are simulations that support this to some extent. And also, one thing that I liked about this is that it reminded me about Kolmogorov's power laws, and there again you need to take care when you interpret this kind of power laws you should only take parts of the Fourier spectrum, not the very end tails, not the small frequencies. And the interesting part is that Bray claims that you can get something like this on a very simple system, right? So for me it was also exciting because it looks like poor man's Kolmogorov law, right? So you can try to get those things in a simpler system, okay? So
you assume that the islands are spherically symmetric because you have only one distance.
well, I don't know, to be honest, what he assumes.
Otherwise you would have an L parallel, L perpendicular, something like that, I guess.
In simulations, it looks like this. Let me show you. Simulation, which seems to get close to what this guy was saying. This is actually work done by Julia Yomas and collaborators. So they have this Schlieren pattern, and in here the Schlieren pattern is the one shown in the colors, in the shades of gray, right? And you have that the black and the white islands have directors perpendicular on each other, okay? And then there are the arrows; those correspond to the fluid, okay? So you have these Schlieren-like patterns, and if you compute those quantities, she got the correct scaling for, the predicted scaling for the correlation function. Things are a bit more complicated for the scale factor for the Fourier transform. But the interesting thing, she did these things for coupled Navier-Stokes-Swiss Q-tensors, but the interesting thing is that she says that fluid doesn't really play a role. On the other hand, that's also what Bray says, that the simplest gradient flow of this energy, which is these equations, my favorite equations from yesterday, but now dynamical, can capture that behavior that was claimed before. Okay, and then he tries to derive intuitively a Porot's law, and he says that, well, when you have this kind of uniaxial form, which you should have most of the time, this behaves overall like something that depends on a unit vector, and then you have this O3 invariance in the energy functional. So this should behave overall like, this should provide you a Porot's law with the exponent corresponding to an O3 system. And there are experiments and simulations done by these guys, and they also get those Schlieren textures, and when they compute those average quantity, they get that scaling behavior. And well, nothing is perfect, so they seem to get O2 kind of scaling in that structure factor rather than O2, than O3, and they say that's because of the presence of string defects. Okay, so that's what they have. And then there is a huge controversy. First, these guys, at about the same time as the article, they suggest heuristically that this LFT should, so this is the average size of nematic islands should grow like square root of t. And then, there was a competitor that, another group that, were saying that, probably the defects actually make things worse in the sense of violating the dynamical scale. And then, some more controversy. Then some people got these logarithms. And nevertheless, the state of the art seems to be that you do get this power law for this quantity L of t. So, both in some experiments and numerics, and in these more recent numerics. So what this group says is that if you wait long enough, essentially things will behave as they were supposed to. Okay, so things are very controversial overall, right? And at some point I tried to invite Bray to give a talk, and he was saying, well, I don't really know if things are still the way I was saying at that time, but yeah, qualitatively maybe things should be like that, and probably Julia Yomas is the one that understands things as the state of the art, at least as it is now. Now, what can you do mathematically? One thing that was interesting to me was this average over initial data, because there is no general mathematical framework for that, but there is something for turbulence, right, where you try to avoid the anomalous behaviors, and there is this idea of statistical solutions created by Foyash and Forsikov and Vishik around 70s, but Foyash was first, where the basic idea is that you look at all initial data, and you look at a probability on it, and then you are this is the probability, don't worry about what I said, and then you can evolve this probability by the flow in this sense. The probability of the same set at time t will be the probability at time, the initial probability, but now measured along the flow. And you can, this requires having a well-defined flow, but you can define these measure solutions even if you don't have a flow, like in Navier-Stokes when you don't have uniqueness. But apart from that, just think of this as a mathematical tool that allows me to make sense as to what happens over initial data, and average to get rid of the possibly anomalous behaviors. Yeah. So my correlation function would be like this, as advertised before. I average over the x's, yeah, and then I get just a quantity on R, and then I average over all possible initial data, this thing here, and I normalize things. Okay, so that's my correlation function, which seems to be, what was advertised. It should be said that also there are some variations in this definition of the correlation function in the literature, in the physical literature, but yeah, some small variation. Okay, now if you think about that simple gradient system, the question is, what can you understand about it? And since I have this thing here, I can't help but using it. So you have something like this. So, for all mathematical purposes, this is a pretty trivial system. So, I was very excited when I heard that you can get something like a Kolmogorov type law for this kind of system. Of course, I can't actually prove it, but hopefully one day, if this is actually true. But what can we do? So, what happens in this kind of system? For instance, if you start with initial data Q0, which is diagonal, the simplest kind of thing, well, then it reduces to a scalar equation, something like that there. And that's a very well understood equation. And it's very easy to understand what happens also at an intuitive level. So this is the so-called reaction diffusion system, and this part here is a gradient. And there are like two possibilities in terms of what f can do. So you have this kind of behavior for the energy. So this is the case when you are with your temperature above the supercooling temperature. So isotropic is locally stable, and so is nematic. If you go deeper in the nematic, you have one unstable local minimizer and another stable global one. Yeah. So that's what the F does for you. And then what does this dynamical system produce? Well, if you just think of simulating it numerically, you do a splitting step. Yeah, I think it's called splitting step. Anyway, you do this procedure when you first solve the heat part, and then you solve just the other part, ignoring the Laplacian. Yeah. So if only the heat acts, then you have like decay towards zero. If the other part acts, it depends. If you are in one of these potential wells, you'll go to zero. If you are in here, you'll go to the nematic. So this is what I call the shallow quenching regime, because you quench from a temperature which is very high to one which is still above the supercooling temperature, and this is the deep quenching regime. So you need to have a bigger jump in the gradient of the temperature. Okay, so overall there is this competition between reaction and diffusion, right? So if you imagine that you start with some initial mass, yeah, the reaction will try, so the Laplacian part, the heat equation, will try to spread it out and make it go to zero. The diffusion part will try either to make it go to zero or to a nematic. To zero if it's close enough to zero, otherwise to nematic. So this is actually the regime that we withstand to some extent, the shallow quenching one, when the isotropic is locally stable. Okay, so if you write explicitly what the equations are, you get this term that you know at the scalar level now, and when A is greater than zero, so after a suitable normalization, suitable non-dimensionalization, remember that has a tendency of always working with non-dimensional quantities. So for A positive you get this picture, for A negative you get this picture. Now, so I told you there is this competition between reaction and diffusion, and mathematicians kind of understand what happens, at least in a simple case. So there is like a sharp transition between the case when the reaction wins and the diffusion wins. Namely, if you start with your initial data, which is something like this, yeah, so it's 1 on an interval minus L. If the reaction were to act on it, it would go down, yeah, to zero, to spread it out. If the diffusion were to act on it, it would stay the same, because in here one would be like nematic, yeah. So when they have to compete, well, it depends how much mass I put here. If this L is large enough, then this keeps spreading. So reaction wins. If this L is small enough, then diffusion wins. And the interesting thing is that there is this rare behavior, there is this special balance when neither the reaction nor diffusion wins. So this thing, the solution goes to something which in the whole space looks balanced, a stationary solution. Yeah. So this is anomalous. This is for L is equal to L naught. And even understanding that this anomalous behavior exists is a big thing. I mean, it's hard, okay? This is a very good mathematical journal, and it was done only in 2006. Okay, so there is this balance between reaction and diffusion. What can we do? Well, so first you need to take care of these statistical solutions, but the good thing is, of course, you can approximate them with essentially convex combinations of individual solutions. So, you know, if you understand what happens the individual solution, you use these averaging mechanisms to eliminate the rare behaviors. But, you know, this is the most naive thing that you could do with these statistical solutions. Ideally, you'd hope that there is a way of working with them without knowing, without having to deal with the individual behaviors. And that's really what you'd like to do, but we're not anywhere close to that. So what can we do? For small enough initial data, and small enough means in here that the L2 norm, so L2 norm is not a scary sound. What? Small enough.
From J, no, the top equation.
Yeah.
From J running 1 to small l, right?
No, J of n.
Yeah. And is it something cutoff?
No,
Cutoff?
no cutoff.
What's that?
It's just a convex combination. It says that those numbers add up to 1.
We don't run n to infinity.
You run n to infinity, but also for each n, you have jn elements in that convex combination.
How n is fixed, determined?
No, it changes. But we'll get there. We'll get there. Okay, so for small enough initial data and for any solutions, you can show this thing, which intuitively is quite a triviality. So for one thing, you can ignore this term here, and you see that this is like the heat kernel plus something that decays faster than the heat. So what this thing is saying is that for small initial data in L2, so L2 just means that, well, this this quantity is small. So on average, the initial data is small, so reaction is expected to win. You have something like that. So, you know, if you wait long enough, the nonlinearity won't matter, and it will behave like the heat equation. So nothing, you know, weird here. Now, this only happens if you have this term here that is non-zero, and don't really know. At least we don't know what happens in general if that's non-zero or not. But if it's non-zero, so you know, if the heat-like behavior dominates, you can put that representation formula in your formula for the correlation factor, and you get that the correlation factor has this scaling behavior, right? Where you see you have like r squared, and then you have t there, right? So you get that L of t behaving like square root of t. But now this is provided that you have heat-like behavior, and we don't really know how often that happens, right? How often is when you have troubles, when you have presumably rare events. What we can show, though, is that you have an analytic map from the initial data to that matrix. So, no, being a real analytic, well, in this infinite dimensional setting, this means that it behaves essentially like a complex valued function. You know, for complex valued functions, the zeros cannot accumulate. Yeah, they have to be rare events. So, in this sense, the cases when you have trouble and this is actually equal to 0 are rare events, so suitable averaging will ignore them. Now, I don't know if this is in general the case or it's just that we cannot do better, but at least if you had a nonlinearity here, which is, you know, mean 0, like in Navier-Stokes, for instance, then you could show that heat equation always wins. But in this case, you can only show that heat equation wins most of the time. So, what do we get? For small initial data, you get this predictive scaling, but that's a true disappointment in some sense, because also the method that we use also shows that what you really see is just the heat-like behavior. It has nothing to do with this part, where presumably the information about nematics should be important. So in order to take care of this part, you need large initial data, and that we don't understand yet in general, but only on a very special case, in the scalar case. And then what happens in the scalar case is the following. Okay, let me give you the picture of what's there. So what's there is, if you start with something like this, it will, so this is like 1, and this is eventually exponentially decaying. This initial blob will increase, and 1 goes all the way towards filling the bubble space. Okay, so later times you have something like this. And there is some story there about traveling waves, which is to say that if you cut and look at just half of it, that's like a traveling wave. And for this kind of behavior, you get a different scaling. You get R over T. So L of T is like T. Yeah. Now, so you get this type of scaling that doesn't appear in the simulations, but under very restricted circumstances, you don't know how generic this type of behavior is. But if you were to work with those special initial data that Latosh had, you see that there is a competition between two types of scaling. There is this heat-like square root of t scaling, and then there is the scaling for large initial data. So what happens if you take initial data that are in both of the two worlds? Well, if you just average over these heat-like behavior initial data, well, you do get the heat scaling. But if you put just a little bit of large data, this and you average, the large data behavior wins. No matter how little of no matter how little of this large data behavior you have. Now, don't really understand what happens and why you get this scaling, and that scaling that you get is really just capturing part of what this system can do, namely capturing the scalar-like behavior. So you don't understand what happens, if there is a proper scaling that is not scalar in nature, but this equation, because this system, because it's a system, knows more tricks than just the scalar. So you can get different scalings maybe different from t. Okay, so what's the story? You have very interesting problems that are related to this simple-looking equation. What we can show is that you get this square root of t behavior for that quantity L of t, but this is a disappointment because that's related to the underlying heat-like behavior. It doesn't really capture the nonlinearity. If you want to see the nonlinearity, you need a large enough initial data, and then you get that scaling like t. But really, we know how to get that only if we use little of the equation, just the scalar, a scalar form of it, if you want. We don't really know if you have, if you have like the full equation, if you start with something which is not of this form, you get different kind of scaling. So this is very interesting for simulations. And yeah, we would like to understand what happens for large initial data when you have a matrix which is not of this form, and also study the structure factor, presumably in the limit when L tends to 0. That's the better thing to do in order to get those predictions of Bray, if possible at all, if the equation wants to do that. So you see, I have plenty of questions and very few answers.
Maybe now I should ask people to give answers instead of ask questions.
Yes, that's what I was hoping, but you can ask questions.
So I guess the assumption of small data, initial data, might be okay to get a second order phase transition, where if you just cross the phase transition, you can assume that just a small perturbation of your...
Yeah, I mean in principle this Q-tensor story is supposed to hold, right, for small data near, right.
But obviously here you've got a first order phase transition, so unless B is very small, then you can't assume small data.
So you're saying it should be on this large data?
Probably close to the spinel group. I mean, this is coarsening and dynamics. It's the spinel that plays a role of where you lose the stability.
So yeah, I think what you're saying is that you get this kind
call
of,
it the
you have this large nematic island growing overall.
Yeah.
But
Well, you'd expect fluctuations, wouldn't you? I mean, we expect correlated fluctuations, but very small. And then that's
in the
where
first order.
yes, I mean, as initial conditions.
Oh,
Right.
initially.
I mean, you're worried about initial conditions, and
Mhm.
you're worried in some sense about exceptional.
yeah, I mean you want to ignore those exceptions, right? That's one difficulty. But then yeah, it's not clear to me. So the most interesting question is because it's a matrix, does it know tricks that scalars don't? So I don't know exactly how to shoot for
Well,
that.
there are, two timescales in here inherently. You've got your small fluctuations that come in.
Yeah, but those you want to
around the
average out.
isotropic. Around the isotropic, then grow, forming the nematic phase. And once the nematic phase forms in islands, then that grows in a completely different way. Those are the two growth stages.
Right. I mean, you want to look at the long-term behavior.
Depends what you mean by long time, in a way. You could have a kind of two time scaling here.
Yeah, no, there are these metastable states, as you say, initially, when they decide to meld together, and then there is this long time behavior when everything is melded in this big blob and somehow behaves. So I don't know if maybe the hypothesis refers to this metastable situation, not the very long time, but the sufficiently long time. So might be that too.
Do you have any particular calculation, say, in the case that maybe you just don't get, some random domains, but you get something structured, even periodic? Then you could actually have
Well, we tried something like that, right? I mean, if you work in this LP kind of framework, so you assume decay at infinity, you can't really have periodic. But we tried to see what happens in the periodic case, and that's kind of weird. Because for one thing, it seems to evolve to a stationary state, and then there is no scaling. And for the other hand, I don't really understand how people did the simulations if they didn't assume periodic boundary conditions, right? Because I tried to convince some people to do simulations, but they said, "Oh, but infinite domain." Yeah, how do we do simulations in that case? So. Yeah, on the other hand, I'm not yet fully clarified with the periodic case.
So, but how does this fit with, say, very well-known cases like, for example, coarsening of domains in the one-dimensional heat equation? Or another system
In
that
the
would be
heat
very
equation?
interesting to test would be, for example, dipole copolymers, where you have nucleation in several domains, but you can keep some control of them because they are in a way periodic or quite regular. So I don't know if these
Yeah, I'm not
has
sure
any
about
significance at all for these
the
systems, but it seems like a good place to test.
I mean, it seems to be a difference between conserved and not conserved systems. So, Kahn-Hilliard versus Allen-Kahn. So this is like Alan Kahn. Yeah, I don't really know in some sense how to approach this. There are, quite mathematicians that looked at this, but they take a completely different approach. Namely, they say there is this quantity that tracks the behavior of L of t, and we're gonna reduce out of the equation essentially something that we can close, something like on ODE, and then that gives us upper bounds for L of t. But they don't, in some sense, worry about what they can't treat the anomalous behaviors. Yeah.
And also one thing about this theory that sounds a little bit strange is that as soon as you have nematic patterns, say nematic animals and isotropic media, somehow some kind of surface energy should be important. And I don't think you can fit it in a reaction diffusion equation.
Yeah,
so
no, that might be true.
For example, when if there is collapsing of domains or any kind of merging, then definitely the surface energy has a main role. And so this should completely change the scales.
I mean, I completely agree. I'm very happy. I'm very willing, let's say, to say that this is a wrong model. What upsets me are the simulations that seem to get what is claimed, right? So now I'm kind of, I don't really know if this equation actually can do that or something definitely wrong with the simulations.
Just a comment that your L of t reminds me of the distance between two annihilating defects, which actually in dynamics, which actually is proportional to t when the defects are like a very large distance, and it goes like the square root of t when they are very close.
Okay. No, I mean, they say indeed that when they do these simulations, it's very important the way the defects are annihilated. So this might be related. So you said it's proportional to t?
It is either t or square root of t,
really?
depending on the distance.
So where is this?
Well, there was many papers.
Okay, that's very interesting. Yes.
In theoretical physics, this anomaly phenomenon, the more important one is log divergence. Power is something anomalous. I said, and it is related to log divergence. You mentioned some log correction or something. Do you have some singularity that related? No. No log divergence.
No, I think log is more subtlety than I'm capable of getting at this point. Maybe there will be some log.
Our physical physicist view that integer power or something like that is not so interesting.
Yeah.
Anomalous one is interesting.
Yeah.
Integer is simply, usually, I am saying only usual case, simply power counting can predict the number. But most important one is anomalous one is not integer, some real number.
Yeah.
So integer is related to renormalization procedure or log divergence. I'm questioning such a singularity appears in this
No singularity here.
No?
Everything is symmetric.
Okay.
Sorry.
I don't remember what was in Bray's paper, but it was fairly general, wasn't it? I mean,
He had for many kinds of systems, right? But there were like two types, conserved and non-conserved.
yeah.
And then he had some explicitly solvable models. But I was attracted by the fact that he was talking about liquid crystals using those Q-tensors.
People would have
interesting
tested out
prediction.
those predictions for other models, not just liquid crystals. They've tried it out for spin models. And
they definitely happen in many models, right? So there is one issue. If this is good enough model, and then miraculously enough it works in simulations, then I don't know if you are not cheating somewhere there in the simulations, basically I can't really understand what's happening here yet, hopefully.
Any more questions?
So you define random events in this theory as events that happen without diffusion?
Sorry, if?
rare events in this theory would be those that happen where diffusion is not involved. So that rare events in this theory happen when diffusion is not involved.
No, I think you need some kind of diffusion.
But you set up that A and J matrix to zero, so.
Sorry?
You set up that matrix identical to zero, the matrix that has the...
So that's like the degenerate case, yeah?
Okay.
So that's like the rare events when something goes wrong with the arguments, and most of the time it's non-zero, right? So that's when you understand what happens. So the case when it's zero is the degenerate case, and that's rare in a sense.
So it's not a rare event in the sense of an event in an energy landscape.
In a, sorry?
In the sense of an event that happens in a complicated energy landscape.
It's rare in the sense that pretty much any perturbation you take gives you the right thing. But yeah, there is this initial data that don't know exactly what happens. But if you perturb it a little, you can get one for which you know what happens. So in that sense, it's rare.
Okay, well, let's thank Arghir again.